All right, ladies and gentlemen, we are doing linear algebra mastery. Let's jump into our flashcard system, Anki, because it's been a while and surely we've got some Anki flashcards due, but we're about to find out. So let's find out. Nothing is actually due today for flashcards. All right, then, what did we learn about yesterday? Well, we started the section on Gaussian elimination. What is this section all about? This section is all about how to solve augmented matrices, how to solve linear systems using elementary row operations on augmented matrices. So we're just trying to solve linear systems specifically by hand. So they've got to be not super large. They can get as big as you can imagine, infinite variables nearly. You can have millions and millions of unknowns. Can't solve that by hand. We're talking about solving linear systems by hand, so they've got to be small. Solving large linear systems require computers. The rules are how to solve them, the methods of how to solve them are based on the simpler methods that we use by hand, but computers solve them. You've got other aspects to consider, such as memory of the computer, solving time, round off errors. So you've got these other aspects that make it more complex. And if you want to study how to solve very large linear systems, it's studied in the field of numerical analysis, the mathematical field of numerical analysis. Okay, right? So we're focusing on small linear systems that can be solved by hand. Okay. Then we talked about echelon forms. So we've learned about two echelon forms. We got reduced row echelon form and row echelon form. What is reduced row echelon form? Well, reduced row echelon form is a form of an augmented matrix that's actually more specific than row echelon form. So all reduced row echelon forms are within the set of row echelon forms. This is broader. So all reduced row echelon forms are also in row echelon form. Not all row echelon form are in reduced row echelon form. Okay, what is reduced row echelon form? It's an augmented matrix in which if the row is not all zeros, then the first non-zero digit reading from left to right is a 1. We call that a leading 1. That's one thing that makes it a reduced row echelon form. Another requirement is that if it is a row of all zeros, it's at the bottom of the matrix, okay? Another rule. Columns with leading 1s, there's no other non-zero digits. So if there's a leading 1, the rest of the column is zeros, above and below. And the final thing is in consecutive rows that both have leading 0 or leading 1s, the row that is above has a more left leading 1, and the row below has a more, therefore, right leading 1. Okay? That's a reduced row echelon form. Well, what is a row echelon form? Same thing as reduced row echelon form, except for the column, right, with leading 1 doesn't have to have all zeros to be in row echelon form, only for reduced row echelon form. But considering the rule of that consecutive rows that both have a leading 1, the row above has a more left leading 1, and the one below has a more right leading 1. Basically, that comes to the simplification of the difference between reduced row and row echelon form is that columns with leading 1s in reduced row echelon form have no other digits except for zeros. In row echelon form, columns with leading 1s, there can be non-zero digits, but they're only going to be potentially above the leading 1, never below. They're below the leading 1s, and both forms are all zeros. Okay, so that's reduced row versus row echelon form. Once we get an augmented matrix into reduced row echelon form, we can solve just by looking at it via inspection or from using parametric equations. Okay, then we learn about two variable terms. We learn about free variables and about leading variables. Leading variables are variables that correspond with leading 1s in augmented matrices, and free variables are variables that correspond with digits in the augmented matrix that are not leading ones. Cool? I think that catches up to speed. Let's check out and make sure we got everything. Yep. Yep, yep. Yep, yep. Yes. Very nice. Yep. All right. Wow. Wow. Okay, sweet. We got everything. I really feel like I'm getting it so far. Let's continue reading, and I'll be back for a recall in a second. All right, guys, that is the section on echelon form completed. I went ahead and finished reading it, and then I summarized just in one statement, one good statement about what this section is about. So what do we read about? Basically, okay. When we have, when we're solving a linear system in which there are free variables, we're going to want to solve for the leading variables in terms of the free variables, and then set the free variables as parameters, treat them as parameters, and create a parametric equation. Parametric equations are cool because you can just plug in arbitrary values for the parameter or parameters, and then you can solve for the leading term that way and get, the leading term's gonna be based on the values of the parameters. Cool. Actually, I thought parametric equations only work for infinitely many solutions. No, not I don't know actually. Maybe not necessarily. I don't know. We'll have to figure that out as we go. I'm just gonna write that down as a question. 1.2. Whenever I come up with questions, I like to just verbalize them clearly, and then I come back to them later and try to answer them. So 1.2, do parametric equations only work / only solve linear systems with infinitely many solutions? Question mark. All right. So there you go. That's for free rows. When we're using parameters, typically we use the letters R, S, and T. But any letters that don't conflict will work. Anything with more than 3 unknowns, you start using typically T with a subscript. So T1, T2, T3, T4, Tn, etc. Okay, then we learned a term called general solution. So when we have a parametric equation, a set of parametric equations that solves for a linear system with infinitely many solutions, we refer to that set of parametric equations as a general solution. And then for the summary of what this echelon form section was all about, I basically said, if we can get an augmented matrix into reduced row echelon form, then we can solve via inspection or parametric equations. Boom. All right, let's continue reading on. We're now into a section about elimination methods, that's what it's called. So probably won't be able to get through all of it today, probably not, but I'll read a little bit and then I'll be back to recall. We just figured out, or just learned how to solve augmented matrices. Well, at least we learned how to turn augmented matrices into reduced row echelon form. We learned the algorithm, the steps for how to get any matrix into reduced row echelon form. Well, how do you do it? First, we're going to want to get the matrix into row echelon form. Well, how do we get into row echelon form? First, You find the first non-zero column reading from left to right. So when you find, if there's any digits in a column that's non-zero column, you find the leftmost non-zero column. That's step one. Next, you're going to want to move, if necessary, a row, swap a row to get the top row to have a non-zero digit in the leftmost column. Or the leftmost column. We want to get this non-zero leftmost column. We want to get a digit in the top part of it that's non-zero. Okay. Once we have that, then we can basically eliminate everything below the leading one, because we just created that leading one. We can eliminate anything below it by adding multiples of this first row by the rows below it. Then we get these all to zero. Then we lock that row basically into place, ignore it, and now treat everything below it as its own matrix, and repeat the steps. So we find the first non-zero column from the leftmost non-zero column. We get a digit into the top part of it. We eliminate, or we turn that into a 1. Sorry, I think I forgot about that. We get that into a leading 1 by multiplying the row through by basically 1 over whatever this digit is. So 1 over a if this leftmost digit is a. And then we add multiples of this row to the rows below it in order to get zeros straight through below the leading one, and repeat, rinse and repeat until you've done it for all rows. Now you have a matrix into row echelon form. How do we get into reduced row echelon form though? Well then, starting at the bottom with the first leading one, we're gonna add multiples of this row to the rows above it in order to eliminate all digits above the leading ones, one at a time, via the same method as going down. You're adding multiples of this row by multiples, or by the rows above it in order to get them to zeros. And yeah, that's all we learned today. I think this method is called the Gauss-Jordan method, but we haven't read that far. Just kind of looked ahead a little bit, but there we go. We can take a matrix and I can turn it into reduced row echelon form now. I can also turn it into row echelon form, but yeah. Great progress being made here. Yesterday we read 2.5 pages. Today we read 2.5 pages. So yeah, we're kind of moving here. We're kind of ripping. If we keep at this pace, which there's no rush, but if we keep at this pace, we'll be done in about 3 more days for the reading 1.2, and then we'll be into the practice problems. We'll go and interleave some of those from section 1, and yeah, but great progress made today. Talk to you guys later. See ya.